Hello and welcome to our lesson on regular polygons, which include shapes such as pentagons, hexagons, octagons, and decagons. In this lesson, our primary focus will be on understanding more about these shapes and basic theorems related to them. We'll start by defining regular polygons and identifying the key properties of shapes like pentagons, hexagons, octagons, and decagons. Then, we'll delve into the basic theorems that govern these shapes, exploring their interior angles, exterior angles, and the relationships between them. Finally, we'll apply this new knowledge to various examples to solidify our understanding and see how these theorems can be useful in solving geometric problems. In our previous lessons, we've built a solid foundation by discussing triangles and quadrilaterals. We understood their types, properties, and basic angle theorems. Secondly, we have discussed how to calculate the perimeter and area of basic shapes. With this foundation, we are now ready to explore the properties and theorems of regular polygons. Understanding these shapes is crucial for tackling more complex problems in geometry, such as calculating areas and perimeters of more advanced geometric figures. Let's get started. Now that we have covered 3- and 4-sided shapes, let's increase the number of sides and explore polygons with 5 or more sides. Today we will talk about polygons like pentagons, 5 sides, hexagons, 6 sides, octagons, 8 sides, and decagons, 10 sides. We're not focusing on varying the angles and lengths for shapes with more than 4 sides. A regular polygon has equal-sized side lengths and angles. To remember the names of these polygons, it might help to visualize them. Let's start with a pentagon, which has 5 sides. One way to remember this shape is to recall you're holding your pen in your hand. And your hand has 5 fingers, so a pentagon has 5 sides. Now let's move on to a 6-sided shape, the hexagon. To help visualize this, imagine a beehive cell. This is hexagonal. Now let's move on to an 8-sided shape, the octagon. To imagine this, we can think of an octopus which has 8 legs. Our final shape is a decagon. A decagon has 10 sides. Now we have been introduced to these shapes, let's think about how to calculate the sum of their interior angles. We already know how to calculate the sum of the interior angles for rectangles by splitting them into triangles. We will use the same technique for these more complex polygons. For example, let's break down a pentagon. A pentagon can be divided into 3 triangles. Each triangle has interior angles summing to 180 degrees. Therefore, the sum of the interior angles of a pentagon is 3 times 180. This equals 540 degrees. We can generalize this approach. For any polygon with n sides, the number of triangles it can be divided into is n minus 2. The sum of the interior angles is therefore 180 times n minus 2. So the sum of the interior angles for any n-sided polygon is given by the formula. Sum of interior angles equals 180 times n minus 2. Next, let's look at the sum of the exterior angles. This proof is a bit more complex and involves algebra. For any polygon, the sum of the exterior angles is always 360 degrees, regardless of the number of sides. We will derive this using the properties of interior angles that we already know. Let's use the example of a pentagon. Firstly, we know that the exterior angle is given by 180 degrees minus the interior angle. Secondly, we know that the number of sides of a polygon, n, is the same as the number of angles in a polygon. A pentagon has 5 sides and so will have 5 angles. So to find the sum of the exterior angles in our polygon, we simply need to sum up all n of our exterior angles, each of which are given by the formula 180 minus interior angle. We can write this as sum of exterior angles equals n, 180 minus interior angle, where n is the number of angles in the shape. Let's expand this equation. Sum of exterior angles equals 180 n minus n times the number of interior angles. Now we know already that nen interior angle equals sum of interior angles. Therefore, we can write this as 180 n minus sum of interior angles. We can substitute in our formula for the sum of interior angles, which is 180 n minus 2. So, 180 n minus sum of interior angles equals 180 n minus 180 n minus 2. Expanding this and cancelling out 180n from both sides, we get that the sum of interior angles equals 360 degrees. Thus, the sum of the exterior angles for any n-sided polygon is consistently 360 degrees. Let's go back to the pentagon. We have already worked out the interior angles. Each exterior angle is 180 minus interior angle. Therefore, when you add all the exterior angles, you'll find that they sum up to 360 degrees. Let's apply our knowledge to a simple everyday object, a stop sign. To most people, it's just a red octagon on a pole, but to a mathematician, it's a real-life application of the concepts of geometry, specifically regular polygons. An octagon, like the one of a stop sign, has 8 equal sides and 8 equal interior angles. Let's calculate its interior angles. The formula for the sum of the interior angles of a polygon is 180 multiplied by n minus 2, where n is the number of sides. So our octagon has 8 sides. Therefore, we can sub in 8 for n, giving us the equation 180 multiplied by 8 minus 2. This equals 1080 degrees. And since all the angles are equal in a regular octagon, each angle measures 1080 divided by 8, which equals 135 degrees. Next, picture a honeycomb. The cells within a honeycomb are perfect hexagons. First, a regular hexagon has 6 equal sides and 6 equal interior angles. Using our formula from earlier, the sum of the interior angles of our hexagon is 180 multiplied by 6 minus 2. This equals 720 degrees. As before, we then divide this by the total number of sides and angles to find the size of the individual interior angle. Each angle, in turn, is 720 divided by 6, which equals 120 degrees. Now let's consider a larger structure, the Pentagon building in the United States. As the name suggests, it's a 5-sided figure, or a pentagon. The sum of the interior angles for our pentagon is 180 multiplied by 5 minus 2 equals 540 degrees. Each individual angle measures 540 divided by 5 equals 108 degrees. From stopping at an intersection to observing a hive of bees or appreciating architecture, regular polygons are all around us, and understanding their properties gives us a deeper appreciation of both the natural and man-made world. As we move from simple to more complex real-life contexts, we can see how regular polygons and their properties play crucial roles, which could inspire us to further our exploration in the field of geometry. In today's lesson, we explored the properties and theorems related to regular polygons, specifically pentagons, hexagons, octagons, and decagons. We began by defining what makes a polygon regular. All sides and angles are equal. We then examined the internal angle sum formula for any polygon, which is given by n2 times 180 degrees, where n represents the number of sides. This formula helped us calculate the measure of each internal angle for our specific polygons: pentagons, 108 degrees, hexagons, 120 degrees, octagons, 135 degrees, and decagons, 144 degrees. Next, we discussed the concept of exterior angles, noting that the sum of the exterior angles of any polygon is always 360 degrees. This fact allowed us to determine the measure of each exterior angle by dividing 360 degrees by the number of sides in the polygon. Understanding these properties and theorems enables us to solve various geometric problems, such as finding unknown angles and aiding in the construction of these shapes. We also briefly touched on the real-world applications of these regular polygons in fields like architecture, design, and art, emphasizing the importance of recognizing and applying these geometric principles.